Yes.
Whenever you're ready. Good. Maybe I'll see.
Pronto, você tem, né?
Yeah.
Make sure that you unmute. Make sure that when anything talk facing the camera.
Computer? It's a computer.
Yeah. Audio on the video. It's recordings automatically. I'll post it.
All right, guys.
You can get private.
All right. Good morning, everybody. Thank you for coming. We are Team 4 of Dr. Ting's Aerospace Design 2 class, and our team is made up of myself, June Lane,
Austin Board,
Harris Van
John Erickson.
Andrew Burnett,
Brendan Huns, Kyle Stromberg, Jose.
And for this year, we were given the objective of designing and manufacturing the remote controlled airplane that could take off unassisted and fly 3 laps around the flying field, around 7,500 feet in total, and be able to land successfully as well. A successful flight means that no components of the airplane may fall off during flight and no structural damage may occur during landing. Apart from these, we were given several restrictions, such as a weight where we could not exceed 55 pounds in total, and we could not exceed 8 feet in any dimension of the plane. Apart from these class objectives, we had some team objectives because we were inspired by the U-2 spy plane. So we wanted to maximize the endurance of the plane as well as the efficiency of the plane. And we also wanted to eventually fit a camera on this plane and kind of have it like a surveillance drone. And that brings us to our preliminary design. And in the beginning, we needed some estimations of about the weight of the plane as well as the size of the plane. To do that, we started off by getting some sample weight measurements of key components of the plane, such as the motor, the battery, etc. And from there, we needed to get the entire weight of the plane. And to do that, we compared it to the another successful plane that was designed to be 3D printed. They're called the Joker here. And from there, we took the structural coefficient of the plane so that, and we scaled it to our model. And from there, we were able to get a weight of approximately 7.5 pounds. And we wanted to also figure out the size of the wing of this plane. And to do that, we used a metric that is commonly used in the RC community called the wing tube loading. And from there, we used a score which is associated with the flyability and flight characteristics of our plane. In this case, it's 9. And from there, we were able to get the wing size of the plane and then calculate the wing loading. And we also had a specific speed we wanted to have this plane fly at during cruise, which is 55 feet. And from there, we were able to calculate the Reynolds number, or target Reynolds number. And it is at that Reynolds number that we did most of our calculations for the airfoil analysis. And the airfoil analysis was done using a program called Excel Folder 5. And it's a program that uses Xfoil for the airfoil analysis. And it was done using potential flow and boundary layer equations. And from there, it also uses viscous force to calculate drag, and it also is able to predict stall, although it predicts stall at a greater angle of attack than it normally would in real life. And from there, we were able to analyze several airfoils, the Clark Y, Clark Z, SD7062, GOE 389, and GOE 425. The things we're looking out for during our airfoil analysis were a high maximum coefficient of lift, a high lift to drag ratio, as well as a higher angle of attack at which the airfoil will stall at. And with these metrics in mind, the airfoil that performed the best was the 7062, and it outperformed all the other airfoils in all 3 of these targets, and thus that was the airfoil.
Go front camera.
Yes.
Here we have our information on wing sizing and performance. Our wingspan was set to 6.25, an aspect ratio of 8.86. The taper ratio of 0.46 was chosen. These parameters yield a chord, a root chord of 0.875 feet and a tip chord of 0.4 feet. The taper ratio allows for an efficiency of the wing near that of an elliptical wing without any of the manufacturing complexities associated with the manufacturing process for an elliptical wing, like on these right here. The incidence, dihedral, and sweep were determined to be unnecessary to maintain stable flight. This could instead be done through the airplane design, like placement of the main wing and elevators, as well as through pilot control. This means that there's less complexities associated with that design for faster prototyping and design of the sections that are assembled. The Oswald efficiency factor of the wing is 1.013. This was calculated using lifting line theory, and due to the nonlinear trailing edge of the wing, this can be greater than 1. The aileron and flap chord percentages are 25% of main wing chord. The aileron's total span is 50% that of main wing, and the flap span is 40% of main wing. These were chosen from historical and reference aircraft. The factors here combined mean the aircraft will trim at 2.1 degrees while generating 8.2 pound force of lift.
The control surfaces of the plane are attached via CA hinges, as seen on the top right power of the PowerPoint. So the way that we attach these to the plane is that there is a slit located in the middle of the control surface. And each control surface, the flaps, the ailerons, the rudder elevator, and the CA hinges would be able to slide into this slot and then be glued in using CA glue, cyanonitrate, and then it would be able to also then slide into an adjacent slot, which is located in a back plate on the wing or the horizontal stabilizer or the vertical stabilizer, and then it would be able to be glued onto that respective body. And after it's glued, it'll be able to retain in the non-glued section located between between the back plate and the control surface some degree of motion, which will allow for a hinged control surface. And these control surfaces are going to be attached to the main body using control horns, as seen in the bottom right of the slide. These control horns are going to be laser cut out of basswood and then glued onto the surfaces of the control surface. The surfaces of these control surfaces will be sanded for successful adhesion of the CA glue. And then off-the-shelf control rods for control surface connections will be used. These are purchased from an online store. And these will be connected via a servo arm coming out of the wing or any main body, and then connecting directly to this control horn, which will be able to be controlled by the pilot via
Moving on to the conceptual design. First, we'll look at the fuselage. Fuselage we chose to be lightweight and inexpensive. So obviously we chose PLA to be printed out of. We cut up the fuselage in parts so that it could be manufactured on any run-of-the-mill printer. We ended up going with 3 layers of PLA due to structural issues. 2 little layers would make it fall apart. 2 thick would be too heavy. So our total fuselage weighs 17 ounces, which lines up with our weight expectations highlighted earlier. And generally, the fuselage is cylindrical. This is aerodynamic. There's little drag for sharp corners, as well as torsion resistant because it's a circular cross section. Additionally, we do have ribs going along the fuselage that, again, reduce the torsion expected. And we will be having basswood plates at moments of high stress along the fuselage. The empennage following the fuselage is a traditional tail configuration, and all three tails are NACA 0012s, symmetric airfoils. The sizing was determined by these volume coefficients, which are 0.6 for the horizontal, 0.3 for the vertical tail, respectively. The sweep angles were also determined by historical guidelines, so 15 degrees for the horizontal tails and much more smaller, almost 4 degrees for the vertical tail. The control surfaces are 40% size of the root cord, so the elevators and rudders are 40% of the area. Additionally, the ends of control surfaces are throughout the entire cord to kind of prevent stalling entirely. And these are some of the parameters of the stabilizers.
Then we'll go over here. For our propulsion system, our main focus was our thrust to weight ratio. We were aiming for 0.5 to 1 thrust to weight, so about 3 3/4 newtons of thrust. So that led us choosing a badass 2814 870 kilovolt brushless motor paired with the APC 10x6E propeller. This provided us with our target thrust to weight ratio of 0.5 to 1 at 400 watts, with the capacity to reach 0.7 to 1 thrust to weight ratio. And then powering our propulsion system, we have the 4-cell lithium polymer battery that we were provided with in lab and a 50 amp ESC. And then for a further breakdown in the electrical system, we have these as our main, actually all of our electrical components. So as mentioned previous slide, up top we have our lithium ion battery, our 50 amp ESC, so plenty of amperage where we should have zero concerns about frying the ESC, and then the brushless motor. At the bottom, we have our 6-channel transmitter that we were provided with in lab. Match that with the 6-channel transceiver, which will be located in the plane. And those will be powering one, our propulsion system. Using the ESC, we will get proportional control out of that, which will actually fly a plane. And then we have 7 servos located on 4 different channels. We have 3 17-gram metal servos. 2 of those are going to be used for the aileron, and then 1 is going to be used for our front wheel and rudder in tandem. And then we have 2 9-gram plastic servos for our flaps. Those will be located in our wings, also with the aileron servos. And then we have 2 17-gram plastic servos for our elevators.
Yeah. So for the structure analysis of the wing, first thing I wanted to do was find a factor, and that would be determined by our worst case scenario. The 2 cases considered was at max stall angle, and then the second case was the rapid deceleration while landing. We found the stall angle to be the more conservative approach. So from there, we were able to find the maximum lift produced, take our lift over weight, and we rounded up to a load factor of 5. We assumed the wing to be a 10 over beam, not the wing itself. So most of the lifting would be at the quarter cord, and that's where our spar and stringers would be located. So the spar and stringers would be a 10 over beam. We had an elliptical lift distribution assumption, and from there we integrated once upon a shear and twice upon a moment. And our max moment would occur at the root equation there. For our spar and stringers, we chose to use balsa wood. It's used a lot for model aircrafts because of its lightweight and it's very cheap compared to other materials. That is the yield for the balsa wood. Our critical points found were to be located at the bottom of the stringer, because that's where the tensile forces should be located in bending. So that's more important than the top because the top will be compressive. So failure would most likely occur in the tensile stresses. For max bending stress calculated, it was 760 psi, which would give us about safety factor. Our transverse shear wasn't included because it would be located at a different location compared to the maximum bending stress. And this is because the transfer shear will be at the neutral axis.
So we also evaluated the static stability of our plane. So we made the assumptions of linear aerodynamics and small angles of approximation. And in order to be stable, we want the pitching moment and other moment coefficients to be in a certain value. So the pitching moment coefficient is made up of three components, which are contributions from the wing, the horizontal tail, and fuselage. So the eta there, that's just the effectiveness of the horizontal tail because the dynamic pressure there is about like 0.8 of that of the wing. And there's also epsilon, that's the downwash angle. And the factor that this coefficient needs to be is less than 0 to ensure stability. The next coefficient is the rolling moment coefficient, which is contributed to by the wing and vertical tail. So this term for the wing is an empirical term that fits well with the chosen wing dimensions. So this is an empirical one that matches well, and then there's the term for the vertical tail. And the condition for the roll moment to be stable is to be less than 0. And then there's the yaw moment coefficient, which is made of two components from the vertical tail and fuselage. And in this case, beta is a side slip angle and sigma is a side watch. And the condition for yaw is the other way around, it has to be greater than 0. So we use these expressions in our analysis by first choosing ideal pitch coefficient and rolling moment coefficient. So we looked at historical aircraft and we chose values that for these two coefficients that were in between a glider plane and a general aviation plane. And then because roll and yaw are linked, you only have to define one and the other one ends up being dropped out. So the way we use these equations is we fix those values and then solve for the locations of where we wanted our aerodynamic surfaces to be. And here are our values. Just because a plane is statically stable doesn't mean over time it wouldn't end up going unstable over time. So we need to evaluate the dynamics. So we have these matrix differential equations, which show how the velocities and orientation of the plane and their time derivatives evolve. And you have these matrices A and B, and these are filled with the aerodynamic and inertia information of the plane. So this was evaluated in XFLR 5, which we inputted the moments from our SolidWorks model, and the XFLR 5 software uses potential flow analysis to evaluate the aerodynamics. And the eigenvalues of those matrices correspond to dynamic modes that we will see in the actual plane. And the more negative the real component of the eigenvalue, the more stable that mode is. The only mode that was found to be unstable was spiral, which isn't a big issue because many planes in real life are unstable in spiral. And as you can see in the graph, it takes almost a minute to for the roll angle to become greater than 1 degree. So it's expected that in flight, the pilot will naturally be making corrections to avoid that mode. The other mode that may be a concern is the phugoid. So while the phugoid is stable, it takes a long time to decay. And we don't see this as much of a problem because of our analysis. Our analysis was done with potential flow, which means that we heavily underestimated drag. So one of the major sources of damping the phugoid comes from drag. So because we're not taking into account the drag from the fuselage or landing gear, it's expected that this is a worst case scenario. So it's still stable even without all those other drags taken into account. And you can also see that it takes like 20 seconds almost for a whole period of the oscillation. So we don't expect that mode to be a major issue.
And moving on to manufacturing, what have we been doing for the past couple weeks after all this design? We have one of the wings fully manufactured and all three parts of the empennage, which is the vertical tail and 2 horizontal tails. We decided to go with, rather than 3D printing the full wing, we decided to print certain parts and use wood incorporated in it, glue, and monocoat the whole thing. So for the 3D printed parts, we printed all of the ribs, the leading edge, and the back plates. As you can see in orange on there, they're right here. So that's all to make the monocoating have something to latch onto. for the backplate and the leading edge. And the backplate has a slit in it to make it so that we can have a hinge there for the flaps and ailerons and rudder and elevator. All of those control surfaces are 3D printed, and as was previously mentioned, for the control horn, it'll be glued to that. For the spar in the wing, it is going to be poplar wood, or well, it is poplar wood, and the rest of the wood is balsa. The servo mounting plates are put in here, and they were also 3D printed. And the main reason we chose monocoating instead of 3D printing the whole thing is that it is much lighter. We don't have to worry about the skin of the wing being too thin to fail in the print. And it's also pretty easy to manufacture and do pretty quickly. We were able to do this in one night and all 3 other pieces. And it's also easy to edit. So we have the servo plates in there, and we will be able to cut this out to be able to put the servo in there. And we should be able to re-put another piece of monocoat on there, and use heat gun and tighten it back up so that it maintains the shape. As you can see on here, we have a wiring hole here to run the wires for the servos. We have 3 bolts connect to the fuselage, and the 2 stringers, which are near the quarter cord point of the airfoil. Or I mean the 2 spars, my bad. And it's a very similar shape for the vertical tails, or vertical and horizontal tails. Moving on to the fuselage, we have 6 pieces printed for the fuselage already. They have not yet been glued together because this week we are printing the ribs. There should be about 5 ribs, 1 for each connection. We plan to put them at the connection between all the pieces to increase the structure of it so it won't break there. We will be using CA glue or Loctite, which is shown right here, for gluing all these pieces together. All of the fuselage pieces have these little tabs to kind of, there's about 4 of them to help line it up and make sure that it's going to be connected properly and to increase surface area for the glue. In the front 2 pieces up here where the motor's going, there is a flat plate at the bottom to put Velcro on so that we can place the battery there. We need the battery to be fixed somewhere so that it does not slide around in flight. And we made it span the whole front 2 pieces so that we can move the battery forward or backward as necessary for the center of mass. As talking about the ribs and the fuselage, there's going to be wiring holes so that the whole electrical system will be able to run through the entire plane. And the 2 big holes, as seen here and here, are about 6 inches by 3 inches wide, and those are for service hatches. They will be covered up for flight, definitely. The front one is for obviously putting the battery and the motor and wiring it up, and also connecting these bolts into the front fuselage or the wing fuselage piece, and the back service hatch is for screwing in the bolts for all the empennage pieces and all the wiring servo motors.
Here's our information on the landing gear. We chose a traditional tricycle configuration. Due to this configuration, when rolling on the ground for takeoff and landing, it will be stable and return to the direction of motion. For the pilot considerations, this means that during landing, they will do a flare on the rear landing gears, and the configuration can also be made steerable with the front landing gear, which is planned. The construction of the rear landing gear is done using 12-gauge aluminum sheet metal. This is simple and lightweight, and it's easy to manufacture. This reduces prototyping time, and it is also able to be produced in quantities. So, for example, this image here, these processes were done in quick succession on multiple pieces. So there is a primary landing gear and a backup in case something breaks, which for prototyping may happen. The nose wheel is planned to be steerable to assist the pilot in takeoff and landing, in addition to the status, or in addition to the stability offered by the physical configuration itself. And yeah.
All right, so we would like to also give kind of an insight into where the plane is right now. So the current status of the plane is that the, as you've seen before, the empennage and the wings have been manufactured and monitored as seen by one of our group mates, bringing in the plane, bringing in the wing. The fuselage sections are also printed and ready to assemble with their frames. Once they're printed, this is planned to be done this week. The landing gear must be bent to shape and bolted on the fuselage still, as you saw that the landing gear is currently in its unbent shape. This week, we are planning to form the complete shape of the landing gear, as well as attach the front landing gear to the completed fuselage. And then the steerable nose gear is still in the brainstorming stage. What I mean by this is that currently, right now, we have not prioritized the steerable landing gear. Right now, we have prioritized getting out prototype one as quickly as possible. So if time allows, before our planned flight test date, we are planning to implement a steerable nose gear using the 9G servo and the kit that we have currently. And finally, parts required to finish the plane have arrived, so there is no potential delay in manufacturing for the rest of the semester. We have also ordered backup parts as well in case anything breaks during our first test flight, such that we can get a quick prototype 2 out in a rapid fashion. And then we also did weight estimations to re-estimate the thrust to weight with the current expected weight of the plane. These were done using a lab scale. So first comes the fuselage. This was weighed individually with each section and then added up at the very end. This was weighed with the basswood plates as well. So this fuselage weight does include that as well as the expected weights for the ribs, which came out to be 17 ounces. The electrical components were also weighed, which included the ESC, the battery, the motor, the servo, as well as any wires for the receiver that could be included in that compartment, which came out to be 22.41 ounces. The empennage, which included their fasteners, which was put onto the plane, was also measured to be 10.88 ounces, as well as the wings, including their fasteners, was measured to be 24.32 ounces. It's important to note that for the and the wings, this also included the 3D printed control surfaces, as well as the servos that would be included within these respective surfaces. The front and back landing gears were also measured. These were it was measured using the plate that was prepared by Brendan, as well as the front landing gear that's currently in lab. And then the camera was also weighed, which is going to be purchased from Walmart. It is a 2.8 ounce camera, and for a total of 5.2 pounds or 82.7 ounces. And this updates our thrust to weight ratio from 0.5 to 0.73 pound-force per pound. This is higher than expected for the pilot. However, we are not concerned about the updated thrust to weight ratio because this will allow better maneuvering during potential stall, either during takeoff or landing, and will allow for a faster flight time and potentially a shorter takeoff distance, which will help conform to the requirements set out for this problem.
So projected timeline for like our first flight, as mentioned in the last slide, we already have pretty much all our components ready to be assembled, and most of our aircraft components are ready assembled. As far as later on this week, we still want to do servo mounting, assembling the fuselage, and attaching all the components, the wiring to the fuselage, and placing our battery to ensure correct center of gravity, as well as set deflections of control surfaces to prepare for flight. And next week, we'll have our pre-flight testings and hopefully fly by our first prototype.
That opens us up to a Q&A.
Thank you. Great job.
Hey guys, the first thing I sort of that jumped out at me was you guys are incorporating flaps, and I don't think any of the other groups have done that. Flaps are obviously going to add complexity. They add requirement for control. So what do they do for you that you couldn't have done with just a fixed wing?
These were for the pilot considerations. I am the pilot of the plane, and I don't have very much experience flying custom planes.
Okay.
So
And
You make your own life easier.
so we have higher lift to maintain that lower flight speed during landing, especially because we don't want to stall.
Okay. Well, what does that add to your flight speed?
So the main, in my opinion, the main inclusion of for our flaps was for takeoff. It'll be easier to take off with flaps included, which will help me with takeoff requirements, which we thought would be useful to the overall for the project.
You have like a with flaps, without flaps, takeoff speed or distance? Or...
We do not have.
I'd be interested to see that. Is that I mean, just as a your design is significantly different than some of the others, but I'd be interested to see if that's a necessary inclusion or if it's just make a pilot's life easier. But it's a I don't want to say novel because obviously lots of things have flaps, but it's something novel for this class. So on your structural analysis, there were some really good things I saw in there. Each one of you was presenting that.
there's no page number.
Yeah. And yeah, no slide. I wrote that. No slide numbers in your presentation. So but I will say that you had a discussion of load case you consider, which is excellent. I haven't seen anybody else do that. But that is definitely an important thing to be talking about. I would like to see more depiction of the actual structure, right? So when you were talking about spars in the wings, I still at this point don't have a good feel for how those attach, right? We've got spars coming in the wings, meeting up somewhere. But in addition to that, we've got a bolted jump, right? So I don't have a good feel for what the load path from the wing into the rest of the structure is. So I'd like to see some depiction of that. But that said, from what I was able to gather from the wing up, it looks like the aft fastener is kind of in line with your aft spar there. Like,
I think that they're a little bit higher than the spars.
Yeah.
All the bolts are in line, but the spars are definitely a little bit lower on the airfoil.
Well, are we talking spars? Are we talking? To me, a spar is like a full height member, right? But
okay, you're talking about these two? Yeah. Yeah, so the one has two spars, so the tails just have one square cross section.
Okay, so this bolt, there's not really any structure around this bolt here, right? This one is kind of close to your longeron. This one is maybe close to a forward spar, it feels like. But especially this one, like there's nothing here, right? This bolt is either not going to do anything for you, or it's potentially going to break your rib because there's no load path for anything going here. So consider load paths when you're designing joints. But all right, so back to the structural analysis that we saw. You guys talked about your allowable, which was for basswood spars, right? And I think you labeled that a yield strength.
Yeah.
Okay. And yeah, so I was going to ask about the failure criteria there. And then the last thing I'll point out in discussion of structural analysis is I'd like to see things presented in terms of a factor of safety requirement, like what you are designing your plane to, whether that's, if you're designing a commercial military plane, it's probably 1.5. If you're designing an RC plane, maybe it's higher because you're probably more likely to crash it than most commercial planes. So maybe you're designing at 3, maybe you're designing at 10. Whatever you're designing to, set that out and say, this is what we're going to design to, this is what we're going to meet. And then tell me that you met it with a margin of safety calculation, right? You're familiar with margin of safety? Okay, yeah. So use that to validate you met your requirement. Rather than say, well, we designed it, this is the strength we have, and yeah, that should be good enough, right? That's not engineering. Let's see, other sort of structural notes in your fuselage, and again, we didn't get like a good picture of what's going on in the fuselage, but it looked like some of your cutouts had sharp corners on them. As just as a structural detail, we don't like to see sharp corners. I don't imagine you're gonna have fatigue issues with a plastic airplane that's not flying that often, but it's still gonna be a stress raiser. So put a generous fillet in there, whatever you can, kind of afford to, you can still fit tools or hands or electronics or whatever.
Are you talking specifically like service hatches, those big pads on top?
Okay.
Yeah.
Yeah. Anywhere where you can add a fillet to a corner, to an inside corner is good.
What type of plane crash?
Okay. So fatigue can do. Let's see. On the stuff that I'm not as confident talking about, the aero coefficients, I liked how you presented those. I liked how you talked about how they impacted your design. Like you said, all right, we're aiming for specific, specific range in our coefficients, so that's going to dictate where we try to target for our CG, for our control surface, center of pressures, that sort of thing. I like the way you did that. The one sort of note I'd have there is you said this is the range that we'd be in for like a general aviation aircraft or for a glider, right? And those are entirely different scale from what you guys do. So how applicable is that to the design of a small scale receiver?
So our plane has a pretty high aspect ratio, so I thought like it's kind of a glider, but not fully. So like I just thought it'd be like in between a general aviation and a glider.
Yeah.
And there's not many. I guess it could have used numbers of other RC planes, which is something I should check.
Yeah, I think maybe like a Reynolds number comparison is the right thing to talk about there, right? So planes that fly at similar Reynolds numbers, right? Those are sort of a natural comparison. So that I think would help put a better point on that. Let's see. I know Ting's going to talk about this if I don't. The dynamic stability charts were just tough to read from like the font size perspective, also from a color perspective. I know it's hard sometimes to anticipate what's going to be on a projection system, TV screen versus what's on your laptop screen. But that light yellow was like it wasn't there. Let's see. Okay, so you said you have some ability to adjust your center of gravity by sort of Velcro attachment of your battery. Is that the only sort of, other than potentially adding just like dumb weight to the plane, is that the only ability to adjust the CG yet?
From my knowledge, that's what we were going to be using to adjust the CG.
The battery is by far the heaviest part.
Yeah. It should be 1.2 pounds, I believe.
It's pretty heavy compared to the rest of the plane.
Given the amount of room you have to move forward now, how much impact is that going to have on CG?
We think it's gonna have a sizable impact. Mostly because of the configuration of our plane. Our configuration of our plane currently isn't very tail heavy since we have a propeller in the front of the plane.
Yeah.
So our concern with CG placement wasn't too high, but we wanted to allow some range of movement just in case.
So I'd love to see that presented in terms of like percentage, right? So you're targeting forward. If you have the ability to adjust it by 10% of your forward, 20% of your forward, like that would be a good thing to present. And shouldn't be hard to figure out. And then okay, so the last thing I have, you mentioned that you want to build this as a camera platform, and maybe that's further down the line, but what sort of provisions does that have in your current design, and how does that potentially impact future design? I haven't gotten there yet. Yeah. That's fair. Do you have at least like a mass simulator that when you go and do your test flight, we plan to put, would you say like was it a 7-ounce camera? I forget what the Or do you plan to do any sort of simulation of that mass at least for your test flights?
We should plan on doing that, but we were not planning for
that. And then from do you anticipate just having the camera in like a fixed orientation constantly active?
Correct.
Okay. All right. So you don't need any sort of control channel for that. That's all I did.
Yeah, I think overall a great job. The presentation aside and everything, the presentation network. So the first thing I want to comment on is the thing that if they are necessary or not. First one is a steerable nose here, and you also need a service control that. Is that really necessary for our project?
We we initially planned on making it, but it's not really necessary for the manufacturing.
That's why we've sort of put it on the back burner for now to prioritize getting it out of the way. So it's more of a, we do protect one that's successful. We're going to kind of prioritize trying to implement more quality of life into the plane. It's kind of being our secondary goal at the moment. We don't really see the front lane, steerable front lane being implemented for the prototype one due to time constraints, as well as potential weight constraints with the average of the servo.
When we think about something necessary or not, it's not about your time constraint or your prefer or not. I have requirements. If your design set optimized for my requirement, that determines necessary or not. It's not you guys determine, oh, I want to do it.
But you haven't seen him fly.
So it's about my requirements. Yeah, then you can consider if it's necessary or not. And also for your design, same as Tom just commented, the flaps. So right now, based on your analysis, your flap weight ratio is already high. It's higher than you expected. So, and you set the flaps for takeoff. And if you have high enough flap weight ratio, you can like accelerate very fast. Why do you need flaps for takeoff?
We included the flaps because of our original estimate of 0.5 to 1, which was the lower range of kind of estimated or required thrust to weight ratio.
Yeah, now you have 0.7.
Now we have 0.7, which makes the flaps a little redundant in terms of takeoff.
And when you take them off, it's control high.
Yeah.
That'll reduce the weight even more.
But our secondary consideration was flaperons, which from the results of test flight one, we can kind of re-examine the current size of the plane, whether they're still necessary.
Yeah.
With the new thrust.
Yeah. So my concern is that I think Mark's group have flap from last semester, but you know, Mark was a pilot.
Yeah, if I may step in, can you guys hear me?
He didn't have previous experience by RCFA.
Can you guys hear me?
You have a servo control the nose gear, you have servo control the flaps. I mean, you need to work hard. So it's like anything you make more complicated than necessary, it may go wrong. So I mean, again, I have requirement. You optimize for my requirement. You don't do anything you want. You know what I mean? In the end, if like I want to choose one, like a winter is not competition, but just imagine this winter. I want to choose one. I would say I want to choose one that satisfy all my requirements with lowest cost. I don't want to pay extra things for the thing I don't want. I'm the customer. So so that's why we put a requirement at the beginning semester, right?
Yes.
And the other things for can you go to the size airfoil analysis?
Yeah.
Real quick, I just wanted to jump in. I was listening on Zoom. I think it is necessary to have a nose wheel, steerable nose wheel. So I'm glad you guys are considering that, just as a pilot's perspective and standpoint, just because it's very safe to. Yeah, so just as a safety standpoint, taking off from the runway, having steerable nose wheels is definitely very important. Sorry, I just couldn't communicate over that over Zoom.
Thank you. So this one is the same thing. I do not prefer the screenshot from any software to show you because I really cannot see. And the research for the you mentioned that you use 3-layer PA. I'm curious if 3-layer is really necessary.
Well, yeah. So we tried printing with 2 originally, I think it was. Yeah. And it was too thin. It failed and collapsed on itself. Even though we were printing it vertically, it collapsed on itself
with the brim
with the brim
and
the round.
Yeah. I showed the aircraft I made. It was not 1 layer, and it can fly very successfully. So what I mean is that if it's like sometimes it's not like the 1 layer, 3 layers problem is you really need to adjust parameters like temperature, speed, and everything. It will generate different results. So sometimes it's like because when you add extra layers, you add extra weight. If I'm not expert, but if I could make 1 layer for the entire aircraft makes it satisfy, it should work, right? And so you really need to think about like the first sorry not because I my personal opinion is it's too much. If you put like using 2 layers and it's not strong enough, probably you need like play with material filament or the printers. They're like they're different, even a different batch of filament, they're different. So change the printing speed, change the temperature, change everything. Yeah, to make to see if you can make it better. Because for the PAA, I mean 1 layer, 2 layer, 3 layers add extra weight. But it doesn't affect if it flies successfully. But if it crashes, it doesn't really matter. 1 layer, 3 layers, it will crash to million pieces. Right? But if fly, all of them can fly. So that's what I mean. And one thing I'm just curious because it's not about it's like question or anything. I'm just curious. So you guys use a food for the wing. I'm just like if there's option of the carbon fiber tube and the material you choose, why do you think your decision is better than using, let's say, some group use the carbon fiber tube?
It's cheaper, easier per year. So say fraction star.
Okay. So it's mainly for the cost.
Yeah,
okay.
because my console can have spares ready to go.
Okay, yeah, that's true. And also for your structure analysis calculation, I mean, you just mentioned that you use the good fracture strength for the calculation, but when you calculate normal stress for the bending, it's actually the stress at the bottom, really at the bottom of the wing at the root, right? But your root is around the neutral surface. It's not really carrying that stress.
We have spars. I mean, not spars. We have stringers like at the top and bottom of that location.
Well, all your load though is going through your spars, right? Like the way it's being transferred into the fuselage is through the spars, right? So that's the critical second. And maybe I didn't catch that. I assumed that you were doing MC over I, where I is for balsa wood, cylinder or basswood. So yeah, is that the case, or were we considering weight? Okay, yeah, I wouldn't do that because they're not actually carrying. By the time you get to the root of your wing, all the load has gotten into the spars because that's the only place for it to transfer to the wrist.
So that one.
Okay, this is my first time to attend, so I cannot compare with others. It was a very impressive presentation. The only thing regarding the presentation that I want to mention is it's dry. I did this, you did this, he did this. You need some storyline. Good presentation is all about we are making amazing airplane. And what are the challenges and how we overcome it? You need to make your own story, and all of you need to follow the storyline smoothly. That's the best presentation. So, and having said that, what happened if they build a plane fails?
That was another one.
We fail.
Oh,
You fail, right? So that's the risk.
For the next year.
That's the risk that you have. Actually, in the airplane, they design it, build it, fly, fail. That means the casualty of the human, right? So what can you do since you didn't finish yet? So you have some time and effort. what can you do to prevent your final stage failure at this point? What would you do and what can you
Reinforce the fuselage.
I mean, how do you know your fuselage is already good enough, more than enough, or less than enough?
To test it, not in flight, but
Test it. So no airplane company build airplane and fly and say, wow, we're successful. Okay. That's it.
Basics.
When they make a wing, they test the wing, make sure that the wing doesn't. Of course, you cannot test the entire airplane, okay? But wing, they do it, and servo, they do it. So each component-wise, subsystem-wise, it's a very systematic way to test it to make sure at least that component, you're sure that it's not fake. Only if it fails, they need to make interaction or interface during the assembly can cause the additional problem. But at least at every stage, they make sure your fuselage is not fake. Everything common failure is the wing pointing out from the fuselage to the flight, and the landing, your landing gear is not strong enough that your fuselage damage on the ground. So this kind of thing in your presentation, you simply say it's easy to manufacture it, it's to make it cheap, but it's more than the convenience. So it would be nice if you guys think about how can I prevent my final stage failure. It's called a certification test. Okay, before you get there, what can you do at this stage? That would be a very important thing to do. And in the first slide, you mentioned that your team goal is efficiency and endurance with the camera. Just be careful about what you want to say, because when you say it, then you need to, we are not, we don't do this one for the hobby. We are engineers, we are part of the scientific community, right? If you say that, then you need to prove to show your design is endurant than the others or efficient than others. It's not saying, well, we built it, it's efficient. How can you claim it? It's something that the casual talk, but we need to have some quantitative way to assess. So if that's your goal, if your team goal, ideally like endurance and efficiency, perfect, but have some mechanism or metric to show why our airplane is efficient, why it's more endurance.
Be careful when you do it because Ting's going to say, why didn't you optimize for your 3-lap? Right? If you can fly 30 laps, like you could have saved weight on the battery. Like there are a lot of trade-offs between like what you think is a nice to have in your airplane versus what your customer wants it.
Last one is you did many analysis like here based on initial planned configuration, right? But at the end, you show that your mass is different, your length is different, right? And do you do any kind of iteration to recalculate based on your configuration, recalculate it and assess that it is something acceptable? Design cannot be done by initially you calculate it and then go through it. It is always the iterative process. You did it, and then actually the product is slightly different from what you designed it, and you recalculate it to make sure that your final product is what you expect. So do you plan to do any iteration on your calculation?
We should plan on doing that. It'll be for stability.
Yeah.
That would be a big factor. That has some
dynamic stability. So there was like the initial mass, and then there's like the mass you predict now. So the values used for dynamic stability is on a SolidWorks pad, which is already kind of in between the two. But it's a good idea to re-update it once we have better mass values.
I'll say as a person working in the industry, there's constant rework as designs evolve, right? I'll sit down and do structural analysis, and then somebody say, oh, actually, we need to cut a hole here to run hydraulic tubes or electrical wires, and so now we have to go reanalyze that part, or it turns out that this manufacturing process that we thought we could make can't actually make it work, so we need to redesign it. It's like that is just the constant nature of real world engineering. And so yeah, be prepared for that as your weight evolves, and your weight will always evolve, right? That's going to affect stability, that's going to affect loads, that's going to affect just a whole host of be prepared for that. Don't worry.
I think that's all, but it was a great presentation. Okay.
Thank you. Great job.
Thank you.
Thank you.
You from DBF?
Me right now.
Okay. That's good because after that,
Thank you.